Okay, so hello everyone. Thank you to the organisers for putting on this excellent conference. So the title of the conference is Random Walks on Symmetric Structures. So I think I might win the prize for my title being most relevant to the title of the conference, because I'm going to be talking about a random walk on the symmetric group. But I fear I may win the anti-prize for relevance of the content of my talk to the content of the conference. I won't tell you what I'm talking about, but I'm not talking about groups. The punchline for that will come about 5 minutes in. Okay, so everything I talk about today is based on ongoing joint work with Christina Goldschmidt, who's in Oxford, but is based on lots of history that I'll try and explain as we go. Okay, so the starting point is the following Markov chain on the symmetric group. Let's say we start from the identity, and one step at a time, we pick two elements uniformly at random and transpose them. And we do this repeatedly, and we keep track of the permutation that this induces. So because of the questions we're going to be interested in, I don't really want to track effects involving periodicity. I'm not interested in the fact that that will alternate an odd permutation, an even permutation, an odd permutation, and so on. So I'm going to turn it into a lazy chain by occasionally allowing the transposition that I apply to be the identity. So I was going to draw this on the board to have a nice, very easy start while people could digest their coffee, but I think it'll be less helpful if I use this 1 foot of space. But so imagine me drawing a 6-stage diagram of how this process works, but it's not going to make any difference because it's reversible, but it'll be a bit helpful for the diagrams later if you think of the transposition AB as substituting the labels that are currently in places A and B. So this is A and this is B. If I'm going to apply it, then I swap whatever labels are currently there. There's an alternate way, which is you swap the locations where labels A and B currently are, but this doesn't make any difference. But if you do what I say, the diagrams later will make sense, and if you don't, they won't. Anyway, so because it's a well-behaved Markov chain, we know it has an invariant distribution, and clearly the invariant distribution is going to be the uniform distribution on the symmetric group, on all permutations. Okay, and there's much that one could say that's interesting about this model, but probably the first really famous, really interesting thing that was said is the theorem of Diaconis and Shahshahani, which was proved using an exotic set of techniques from wide ranges of mathematics, especially representation theory, in which they study the total variation mixing time for this process when you're studying it on a large addition of the symmetric group. And they show that there's sharp cutoff for this process in this total variation sense after you've applied roughly order n log n transpositions. In fact, it's half n log n. So total variation distance measures some interesting aspects of distributions, but it doesn't capture all aspects of distributions. So it's worth asking, what property of the distributions is it that sort of finally gets close to uniformity at exactly around the time half n log n? And in the case of this model, it's actually counting the number of fixed points of a permutation. So a fixed point of a permutation is how many elements A there are such that f of A is equal to A. And you can see that in expectation, the number of such fixed points in a uniform permutation, it should be exactly 1. But if you start from the identity and start applying transpositions, a sort of coupon collector style argument tells you that the expected number of fixed points you have is going to be like significantly higher than 1, or well, it's going to be higher than 1 at all times before that time. So there's absolutely no chance that you're going to be close in a total variation sense before then. Once you get to that time, by a coupon collector argument, it turns out you now do have the right number of fixed points and everything else has worked out fine as well. So that's why that's the mixing time, very heuristically speaking. Okay, but one thing we might want to study is the lengths of the longer cycles in such a permutation. So let's attack the uniform distribution first, because that's the limit. And it can be shown fairly straightforwardly that this has a scaling limit in distribution, and most mass is contained in large cycles in a uniform permutation. And the limit is this Poisson-Dirichlet distribution that's defined as follows. So we only need to study one set of parameters for the Poisson-Dirichlet distribution in this talk, but this crops up in a sort of broader range of combinatorial probability problems. But we're just studying the version with parameters 0 and 1 today. So here's how you construct it. There's something missing from this equation. I'll say what it is in 1 second. You take a uniform 0-1 random variable. So we're going to construct a random partition. Okay. So we're going to start by taking a uniform 0-1 random variable. That's going to be one of the parts. And then what's left is 1 minus that, so 1 minus u1. And then we're going to iterate the procedure on what's left. So we take an independent new uniform distribution and attack what's left with the second uniform. So that gives us the second part, and we continue. So that gives us a random partition of the interval 0-1. The problem is, based on the way I've set up this notation, I want this to be in decreasing order of size. So if you can just imagine that I didn't do this in a rush and had a little downward arrow at the end, meaning I finished this procedure and then I put all the parts in descending order of size to get a partition of 0-1. Okay, so why should this be the limit of cycle lengths in a uniform permutation? So I think it's most helpful to think about the element that's called 1 and think how large its cycle should be. So this is a good exercise to set your first year undergraduates. You can show that the length of the cycle containing the element called 1 is uniform on possible lengths 1, 2, all the way up to n. You could just write down what it is, and it cancels. Okay, but once you know how... So, I mean, it's non-asymptotically independent as well. No, it's independent before you get past to a limit. Okay, so once you know how long the cycle containing 1 is, that has some elements in it, and then what remains is also a uniform permutation on what's left. That was what I was going to say anyway, but does that answer the question? Okay, so just to recap, if you study the length of the cycle containing the element called 1, that has some length. What's left, conditional on what you need to condition on what's actually in the cycle, but conditional on what's left, you still have a uniform permutation. So you iterate the procedure again, and clearly that passes to the limit. So that's why you get this Poisson-Dirichlet distribution showing up as the limit of this, as the scaling limit of the cycle lengths in a uniform permutation on n. So on the first slide, I wrote down what's known to be the total variation mixing time. But one could ask, on what time scale do you start seeing convergence of the largest cycle lengths to what we know is going to be the limit? Because it's not a priori known, or not a priori clear that that's going to be at the same time as the total variation mixing time. It might actually be much earlier. And that's roughly speaking what turns out to be the case, but we need to be a bit careful about exactly how we set it up. Okay, so this is all a really famous, a really nice to read paper by Oded Schramm from 2005, and some parts of the argument were done in a slightly more general setting, and a couple of parts of the argument were streamlined in the same paper by Nathaniel Beresticki in 2010. Okay, so the non-interesting phases first. So T represents time, so I guess I've, without telling you, moved to a continuous time. So we're now applying transpositions uniformly as a continuous process. So up until time a half, so when we've added like noticeably fewer than n over 2 permutations, it turns out that the largest cycle is small. Okay. I'm going to scratch that comment. We're not doing it in continuous time, are we? Sorry. If you're happy thinking of it in continuous time, that may be helpful, but there's actually no reason why this needs to be in continuous time. I guess I just didn't want to have a separate case if n is odd. Sorry, does that clear the confusion? Okay. What the floor of Tn it means is n over 2 unless it's odd, so I don't want a second bullet point. Okay. So when we've added noticeably fewer than n over 2 transpositions, the size of the largest cycle is sub-logarithmic in the number of elements. That'll turn out to be not so interesting. And then when we've added n over 2 elements, or a little bit either way to be discussed, it turns out that the largest cycle is on the order of n to the 2/3. Again, we're still not into super interesting things yet. But the interesting result due to Schramm is that after that, so if we're now looking at, I don't know, let's say we've added 2/3 n transpositions, we now have the following slightly complicated situation where we can see Poisson-Dirichlet 0,1 somewhere amongst the cycles. We can't actually see it everywhere, but we have some subset, some like positive mass subset of everything present, and on this sort of fixed class, we have some cycles, and rescaling by the size of this class, that converges to Poisson-Dirichlet 0,1. Question? It means it's tight in probability and bounded away from 0 if you rescale by n to the 2/3. As in, it's order n to the 2/3 in probability. So, I mean, it's the same as big O, but it's not allowed to be, like, too close to 0. Okay, so this is the result of Schramm, and the approximate proof method is to consider time half plus epsilon and show that what you have on this property on this thing on the left-hand side is you can't immediately show it's Poisson-Dirichlet 0,1, but you can show that it has some macroscopic stuff in it. And once you know that it has some macroscopic stuff in it, if you run the dynamics for a bit longer, all of this will be made a bit more clear later, then at any time after half plus epsilon, you do have Poisson-Dirichlet 0,1. So this is going to underpin some of what we do, so I'll give a bit more detail of that in the coming slides. Okay, so I said I wasn't going to be talking about groups in this talk, and if you know a bit about random graphs, then some bits of what's appeared on the screen so far may be slightly suggestive, and if you know a lot about random graphs, probably a lot of what's appeared on the screen so far seems very suggestive indeed. But before explaining that analogy, I'll come to the punchline of the talk straight off the bat, which is what we have shown. So up till now, we know that some subset of the cycles, they converge to Poisson-Dirichlet 0,1 at time half plus epsilon for any epsilon. With Christina, we can show exactly when this effect appears, and it appears in a sort of critical window for the number of transpositions given by half plus an order n to the minus a third correction. And as I say, if you know a bit about random graphs, this will continue to be familiar. So that's the goal to show. And we do know that it doesn't happen any earlier. We can show that as you get towards the tail of this critical window, you see Poisson-Dirichlet, and we can characterize the distribution at other times in the critical window, and you don't have Poisson-Dirichlet. So that's the goal of the talk.
So, to make it more clear, so you are talking about the distribution cycles along central path of this transposition level.
Yes. I mean, we're not stating a process result. We're looking at so at all times n is going to infinity, and we're looking at sequence of times like indexed by n, but I have control of what that sequence is, and I'm going to declare that it's somewhere in the critical window.
But you are talking about product of random
Correct, yes.
Why are you not looking at the process?
Because we'd like the paper to be less than 50 pages. I mean, that's for the future work slide. We haven't written it down. If we do, I feel we know what the result should be, but there are going to be questions Can I answer this question at the end? Once I have some diagrams that might be useful. Okay, I'll answer that question at the end. Okay, so there isn't much board space. I was going to draw this on the board, but I think I shouldn't draw it over there. So you're just going to have to imagine this. Basically imagine the vertices of a graph representing the elements of the space, on the set to which we're applying this permutation. Okay, and every time we apply a transposition, we faintly draw in a little edge with two arrows on it between the places that we're swapping. Okay, so imagine you have 3 transpositions applied up here and maybe 1 transposition applied down here. You've literally drawn a graph. So in order to recover the transposition process I care about, what you need to know is the order in which you applied these transpositions. Okay, but nonetheless, that just by waving my finger, I've defined a coupling between the random graph process and the transposition walk, where I need to supply a little bit of extra information if I want to recover the permutation, but I can say something crude, which is that if I have a component of the graph, when I now consider the permutation, the component of the graph corresponds to a union of cycles in the permutation. So if I have one component up here and one component down here, maybe this guy decomposes into 2 or 3 cycles, maybe this guy is just 1 cycle, but there's definitely no sort of cyclic interaction between the two of them. So, in other words, the permutation gives a finer partition of the set than the component of the corresponding graph. So that's going to underpin essentially everything that's going to follow. But the most useful result, at least the starting point for a result, is that if I've sampled the graph and it turns out to be a tree, then the extra randomness I need to add is the order in which the edges of the tree arrived. But there's a result by Dinesh from the 50s that says, irrespective of what order the transpositions arrived in, the cycle, so cycle is going to be an annoying word in this talk, because graphs have cycles and permutations have cycles. I'm going to try and just say cycle for permutations, but if this is confusing, please do ask at any point. If you study the permutation induced on a tree, it's always a single cycle, irrespective of what order the transpositions arrived in. And if you're bored later in the talk, you can try and prove that. It's quite a cute problem. Okay, so here's a diagram I hastily drew during the interval. So when we study a random graph process, and we're interested in the sizes of the components, one aspect that's useful is that often we don't care about the graph structure within components. If I currently have a component over here and a component over here, and I know their sizes, and I want to know what's the probability that the next time I add an edge, that edge joins these two components together, I don't need to know what's going on in the graph structure within each component. I just need to know how many potential edges there are between them. So if you only care about sizes of components, you can think of this as a so-called multiplicative coalescent, where the rate at which the two components get joined is equal or proportional to the product of their sizes. And we can do a similar thing in this process. So the colors aren't very distinct, but if we assume, so it's maybe more distinct over here. So the black sequence of arrows gives you some initial permutation, and then if you can see this sort of fuzzy blue bit here, that's representing the next transposition I add. So I'm going to swap I'm going to apply the black permutation, then I'm going to swap whatever's currently in these two places. And the resulting permutation is shown in green, and it has the effect that we've taken the original cycle of this permutation and split it into two smaller cycles. And if you know that you're going to do this, then the sizes into which you split a cycle of size n, this is uniformly distributed on 1 plus n minus 1 up to n minus 1 plus 1. Similarly, in the other direction, if we add a transposition which over there is shown in green, between two spaces that are currently in different cycles, then this has the effect of merging the cycles. And obviously that's an exact equivalent to the graph process. The rate at which that happens is proportional to the product of the sizes of the cycles. Okay, so if we're just tracking cycle lengths, we can set it up. It's still a Markov process, even if we're just tracking cycle lengths. Okay, so that summarizes the difference between these two things. What next? So, as an example, what we're going to want to do next, as sort of to move towards proving our theorem, is to sample a critical random graph, in the graph sense, and then look at each of its components in turn. And for each critical component of the graph, we're going to take a uniformly random ordering for what order the transpositions arrive in. And then we're going to ask, what do the cycles look like with that ordering of the transpositions arriving? So what we need to do is build up as big a toolkit as possible for start with a graph, apply an ordering to the edges, now study that as transpositions generating a permutation. What does the permutation look like? So the Denesh result shows what happens if the base graph is a tree. So let's study now what happens if the base graph is a graph cycle, as depicted. So we've got to declare an ordering on each of the black edges of the graph, and we want to generate the permutation. So if you think about it, if I want to know which direction I'm going to go if I start at this point, all I need to know is the relative order in which this transposition and this transposition arrived. If this transposition arrived first, then I'm definitely going to start going clockwise. And maybe, just maybe, I'll end up going all the way around, but there's still no harm in depicting this as going clockwise. This forms a well-defined way to draw the diagram. So as a proof by picture, since something definitely has to go clockwise if it's to the left of the smallest, if it's counterclockwise of the smallest label, and something definitely has to go counterclockwise if it's in the other direction relative to the smallest label, then proof by picture, this has to have two cycles. So how to study the distribution of the cycles? So one thing you can do is, if you have a well-stocked university library, you can go to it and there's a book called Combinatorial Chance. And I'm afraid I can't remember who the author is, but it's a British guy from the 60s that studies, an entire chapter is devoted to this problem in a vast amount of detail. Memorably, the page we found had the 10th coefficient of the generating function in case the first 9 weren't enough. But more sort of concretely, you can study at least the limit by imagining what happens if you increase the size of the cycle by 1, and then there's got to be a largest label appearing that corresponds to the final transposition we apply. And the final transposition we apply, it must send one of its incident vertices clockwise and one of its incident vertices counterclockwise. So what you actually have is a negatively reinforced urn. If you want to move from n to n plus 1, what you do is you pick somewhere to split and add in your extra new edge. And that has the effect of killing one orbit temporarily, and replacing it with two new things, one going clockwise and one going counterclockwise. So this is exactly the same as having a urn full of two colors, where each time you pick out a ball and then replace it with a ball of that color and a new ball of the other color. So that's called the Friedman urn. So if you know about limits for the Friedman urn, you can just read off what they are and stick them into this result. Okay, so I hope that illustrates two hopefully fairly basic examples of what we're aiming to do at a meta level, and we're going to need to do it for critical random graphs. And the key result underpinning this is from this famous paper by David Aldous in the late 90s, in which he proved some results which he calls them folk theorems at the time he proves them. So I wasn't research active then, so I don't know how widely these were known in the community, but he rigorously provides a scaling limit in distribution for the largest components in a critical random graph at any point in the critical window, which is unsurprisingly the same critical window as the one I've proposed for this model, where your order n to the minus a third on either side of criticality. So let me show this picture. So his proof method is to consider an exploration process of the graph where you start somewhere, and as in you start at some vertex, and then you explore outwards, tracking how much of the graph you see, sort of analogous to a branching process. You're sort of embedding a branching process in the graph and seeing how far you get before you run out of stuff to explore, at which point you have to start somewhere else, and the process continues. So roughly speaking, going down below a previous running minimum corresponds to, I've run out of stuff, so now I need to start a new component. That holds in generality, but in the critical window, there's a nice scaling limit that's non-deterministic for what the acceleration process ends up looking like. Let me just go back. So crucially, it turns out that the largest components are of size order n to the 2/3, and this exactly fits when you'd expect to start seeing cycles, or sort of significant numbers of cycles appearing in a random graph, because like the number of potential places where there could be an extra cyclic edge suddenly exactly matches when the sizes of components are n to the 2/3. In the supercritical regime, so sort of when in half plus epsilon and thereafter, you have a positive proportion of the vertices contained in the same so-called giant component. So that's where Schramm's result is coming from. That's the fixed set for his part of the permutation. But before that, so in supercriticality, you're going to have absolutely loads of cycles in the giant component. But before supercriticality, you don't. But it's during this critical window that you start seeing the largest components typically containing a few cycles. Okay, so for our purposes, or at least initially for our purposes, the important thing to note is that there is a distributional scaling limit for the sizes of the components. And in addition, the Aldous result tells you how many surplus edges there are in these components jointly. So a tree has no cycles. Once you start having more complicated connected graphs, it's not really meaningful to say how many cycles does it have, because cyclic structure could be really complicated. So what you actually want to do is count how many more edges than a tree does it have, and you call that the surplus. So if your graph has one cycle, then it kind of is well defined, and you have surplus 1. If you then add another edge somewhere, like within the component, it has surplus 2, and so on. And crucially, this can be recovered jointly in the Aldous result by taking a Poisson process with unit rate on the area under each excursion. So excursions above the running minimum correspond to a component. I guess this guy has small area, this one has slightly small area, and everything else has very small area. But in this picture, there's one noticeably larger component, and it has some area, and the number of surplus edges is Poisson times the area of that in the limit. Okay, so that's our building block. What we're going to try and do is we're going to summon the graph and look at its critical components, and we're going to try and develop the answer to the question, suppose I start with a large, I mean largest components in the critical regime. So they have size n to the 2/3, because in the end, I care about the scaling of the largest cycles, which must come from the largest components. So we're going to try and develop a recipe for telling you about what the permutation looks like if you start with a uniform, large connected graph with given but finite surplus. So I'm not interested in the case where you have a large connected graph with sort of infinite surplus, like would be the limit of a supercritical giant component, but critical components, they're likely to have surplus 7 or 100 or 1,000 or 0, but not log n, okay? So we want to study the permutation effect of that. Right, so this is where we're going to take a very left field turn from the main content of this workshop and talk about the metric limits of large graphs. So I'm going to try not to talk about what it actually means to take a limit, because that's not really my expertise, and also that'll be a bit of a distraction. But one can set up the formalism in the same way that one has continuum limits of discrete trees, so-called real trees. One can also obtain the equivalent thing for graphs with small surplus. It's kind of clear why you can't easily have the same thing for graphs with arbitrarily large infinite diverging surplus, but it feels reasonable that you could have roughly the same thing for graphs with finite surplus. So I need to introduce a little bit of notation. I'm not sure how clear the colors are on this picture to anyone, but this is a stylized example of what a large graph with surplus, let's see, 1, 2, 3, 4. So this has surplus 4. And this is my caricature of what a large graph with surplus 4 might look like. And as you can see, there are a whole load of trees that are sort of hanging off what I'm going to call the core. So formally, to define the core, what I need to do is take all the cycles in the graph, so take the union of all the cycles. If I just take the union of all the cycles, I'm not going to pick up this bit. So I need to actually take the union of all the cycles and any paths that are connecting cycles. But I definitely don't want to include these pendant trees in the core. So I've currently got a decomposition of the graph into a core of that sort of encoding all the cyclic structure and some pendant trees hanging off vertices of the core. Okay. Then, I don't necessarily care exactly how many edges there are going to be in each part of the core. So I didn't draw all the vertices, obviously, but there might be lots of vertices. This might be a long path, and in fact, it turns out it will be a long path. But if I only care topologically what the core looks like, I'm just going to call that the kernel. So once I've deleted all the trees, I have a quite straightforward graph that happens to have some very long paths. And then if I contract all the paths, I end up with a graph with, well, I basically end up with the graph that's been shown highlighted. So with the 6 black vertices and these dark shaded green sort of stubs, but connected up. So I guess they're going to be, if the surplus is k, there are going to be 2 times k minus 1 vertices in the kernel and 3 times k minus 1 edges in the kernel in general. Well, that certainly works for this example, and it turns out that that almost surely works in general. So let's go on. So a theorem due to quite a lot of authors that was initially proved with a very explicit calculation in the early 90s says that if you're just studying the kernel, it's asymptotically almost surely 3 regular. And furthermore, if you go back to the picture, once you know it's 3 regular, it's kind of harmless to take all the kernel vertices and give them like potential out degree 3. So 3 little half edges that have to go somewhere and join up. And the result says, without getting into sort of jargon, that any way you choose to pair up these 1, 2, 3, 1, 2, 3, 1, 2, 3, etc., any way to pair up those half edges into a collection of complete edges, those are all equally likely. So more generally, that's known as the configuration model, and it's important to acknowledge that that was rigorously introduced mathematically by Bela Bolobash in the 80s. And it shows up here as the limit in distribution of the kernel of a large graph that you know has surplus k. So k is fixed and n is going to infinity. Hang on, sorry. Key condition. If you take a... Let's go back. If you have these half edges and you promise to pair them up somehow, it's not actually guaranteed that the graph you end up with is going to be connected. We definitely do need it to be connected in our setting because I started with a connected graph. So sorry, you have to add the condition that that you're going to converge to the configuration model where every vertex needs to have degree 3, but with the conditioning that it has to be connected. We're going to mainly be studying the limit, or at least I'm mainly studying the limit when k goes to infinity, and when k goes to infinity, the probability that it's unconnected goes to 0. So that conditioning sort of vanishes in the limit. Okay, so far in terms of progress, we're up to 1997 or 2000. But the next step is to say a little bit more about what the graphs look like at a metric level rather than just at a combinatorial level. So I sort of simultaneously need this result and the picture. Okay, I'll talk about the result first. So these papers appeared in the wrong order, which is a bit confusing for people who try to read them later. But there's a pair of papers by Luigi Dariberi, Nick Brutin, and Christina Goldschmidt, in which they, between the two papers, give a very complete characterization of what the metric limits for these large graphs with given surplus are. And you can think of that as saying, on top of the combinatorial results from earlier, they give distributions, scaling limits for all the lengths you see in the graphs. In particular, sorry? Initially just, yeah. Well, so one thing they can do is they can give a joint limit for the lengths in the core. So when viewed as a kernel, that's just one kernel edge. But in the original graph, that's a whole load of edges. And conditional on the structure of the kernel, that doesn't actually affect. That's independent of the lengths of the edges that you use. Sorry, that's independent of how many edges you need to turn a kernel edge into a core edge, and they give a distributional limit for those lengths. And I mean, I guess the main thing to say is that they're large. So they're on a scale n to the half. So if the overall graph has n vertices, the lengths in the core are n to the half. So if we go back to the critical window of the random graph process, there the components we're interested in are of size n to the 2/3, because n's a slightly different index there. So in that setting, the core lengths on scale n to the 1/3. Okay, but they also want to know how much tree mass is attached to each of the kernel edges. And so we want to know how many vertices are included at anything between these two kernel vertices, both by virtue of being on the core path and by virtue of being independent trees. And they also have a Dirichlet distribution limit for that, and it's given by Dirichlet half, and there's a very nice Earn argument for that. There's a sort of even nicer, but ultimately a bit simpler Earn argument for the first Dirichlet distribution, because Dirichlet distributions, I mean, the easiest way to think about them if you haven't met them before is what you should get as the scaling limit of a Polya Earn process if you start it appropriately. I guess for the purposes of this talk, the main thing to note is that if k is large, so if we're studying a graph with large surplus, then there are going to be a lot of kernel edges, and the Dirichlet half-half with n parts partition, that's quite a fine partition. There's no danger that, well, I mean, it's very unlikely that you're going to have a part with size a half when k is large. it's very likely that all the parts are going to be uniformly small. And that's sort of the only ingredient we actually need to use in our setting. Okay, so this is the bit that's going to be tricky without a diagram I can abuse, but I'll come back to this definition overview. But what we would like to do, is study. So this is going to be our base graph. So we're going back like 20 minutes to the description of transpositions and permutations. I want to take an ordering of all the edges present in this picture, in the original picture, not in the kernel picture, and I want to order them. That gives me an order to apply transpositions and gives me a permutation. So roughly what happens, so if at any point I'm starting in a tree, at most vertices in the tree are going to get mapped to somewhere else in the tree, and then to somewhere else in the tree. There's going to be exactly one place that gets mapped into the tree, and exactly one tree vertex that gets mapped out. So if I'm studying the total lengths of cycles in the permutation, essentially that's going to decompose into sums of sizes of the pendant trees, sort of glued together based on how they end up sitting along the core. And if we continue to focus on this one, whether this tree ends up as part of the cycle going that way or going this way depends on the relative orders of the three edges, sort of where my finger is. So if you look at the root, that's the vertex that's actually on the core, there are two edges coming into that are core edges, and then an edge going out to form the tree. And what order those three transpositions are studied in determines whether the tree goes that way or goes that way. Okay, so I haven't drawn a tree everywhere, but there will be small trees pretty much everywhere. But the crucial metric observation is that almost all of the vertices present in the whole graph, almost all of them are present in the 1,000 largest trees. So if I want to know things very exactly, I have to take a number bigger than 1,000. But if I want to approximately know where all the mass lives, it's enough to just study the 1,000 largest trees. But crucially, all the core lengths are diverging. So actually, with high probability, all of the largest 1,000 trees are at least epsilon root n apart in terms of where they live on the core. So if I want to know whether this tree ends up going that way or that way in the permutation, that's asymptotically independent of whether this tree ends up going that way or that way in the permutation, because there's quite a long path between their roots. So the orders of the labeling adjacent to their roots are asymptotically independent. And if you condition in the right way and they're not literally adjacent, they're in fact exactly independent. And then we want to do the same thing at the kernel vertices. So there are going to be some trees that, as part of the permutation, end up going sort of towards the top right, and let's say these ones end up part of a cycle that's roughly speaking going this way. So when this cycle of the permutation gets towards this kernel vertex, it's either going to end up, loosely speaking, going up there, or it's going to end up going round. But this only depends on the labels, on the order of the three labels corresponding to these half edges that end up defining the kernel. And that's independent from all the trees as well, because, that's independent from the 1,000 largest trees, because almost certainly there's going to be a distance of epsilon root n between the kernel vertex and the nearest quite large tree. So, roughly speaking, and when I say independent, I mean independent in the limit, we're constructing the trajectories that sort of picture the permutation by, for each tree, tossing a coin to decide whether it ends up going one way or the other way. And every time we get to a kernel vertex, we either need to go clockwise based on where we came in, or counterclockwise based on where we came in. So we're pretty much making an independent half-half choice at each of the significant tree roots and also at each of the kernel vertices. So that's what the following slightly terrifying theorem is going to end up saying, namely that we have enough distributional information about what sizes the trees are and where they live, and for each large tree, we're going to flip a coin. And if we think about this carefully enough, well, this is where I sort of don't really want to go into this, because actually the right way to think about this is by taking a sort of real tree limit. For each edge of the kernel, we know the total tree mass that's assigned to that kernel edge. And it turns out that if I want to know how much of it ends up going one way and how much of it ends up going the other way, it turns out to be a uniform split. So I can decompose my permutation into some sort of trajectories on the kernel, so where each edge is just a single edge length 1. I need to know what that structure is going to be looking like. So that's given by making your independent half-half choices at each of the kernel vertices, so whether to go clockwise or counterclockwise. And then within each kernel, I need to sample the tree mass, that's Dirichlet half-half-half, and then doing a uniform split into what goes in one way and what goes in the other way, and then sort of glue it together using my uniformly independent orientations at the kernel vertices. Okay, so the goal is to attack what happens at the tail end of the critical window, and there's not time to say too much about that, but I can at least give a quick summary, which is I deliberately drew this picture for Aldous' exploration process with a very noticeable largest component. So this is when lambda's very large. So lambda defines where we are in the critical window. So when lambda is really large, we have these fluctuations around a parabolically drifting Brownian motion where, the return time to 0, that's 2 lambda. So that's the idealized return time to 0. So you'll have a bit of random rubbish at the beginning and a bit of random rubbish near 2 lambda, but roughly speaking, the size of the largest component is going to concentrate on 2 lambda n to the 2/3, and it's going to have a lot of surplus edges because it's going to look, well, you can imagine if I double it, it's going to be an even bigger one, and there's more area under it, so more surplus edges. So the number of surplus edges diverges. So the question, if we want to prove our theorem, we need to actually study what happens if we have a large graph with fixed but very large surplus, and then take that to infinity. And our proof strategy is to attack just what you get from the trajectories within the kernel and show that that converges to Poisson-Dirichlet naught 1. So once you then decorate it with the tree mass, as I said, the tree mass for large surplus, it's kind of a fine partition. So if you take a partition that's very close to Poisson-Dirichlet naught 1 and decorate it with something roughly uniform, what you end up with is still pretty close to Poisson-Dirichlet naught 1. And the argument, if I can have 1 minute to explain it, is if you start with your configuration model, so the configuration model where we take our vertices, each of them has 3 potential edges, and then we join up pairs of potential edges to form the actual graph. So one thing that doesn't work as a way to produce the configuration model on 2k plus 2. So I want to construct it on 2k plus 2 vertices, starting with a realization on 2k vertices. And there's a natural attempt to couple this based on just choose uniformly at random 2 edges in your starting graph and then split them to form a sort of bow tie shape. So that means creating 2 new vertices and sort of redirecting things. So it turns out that doesn't work. If you think about it, if you do that iteratively, that's not going to have the right connectivity properties. but it almost works, especially when k is large, and you can couple it so the error in distribution is quite small. However, if you track how long the trajectories are as you do that process, that itself is following something like a uniform split merge process. And as part of Schramm's original result, he shows that uniform split merge, if you apply it often enough, takes you close to Poisson-Dirichlet 0.1. The difficulty with the original model, starting from the identity permutation, is that everything starts in small cycles. In the identity permutation, everything's in a cycle of length 1. If you can show that you start from a situation where pretty much everything is in fairly large cycles, where there's no dust, then this actually works much quicker, and you can, if you know that there aren't too many cycles of size epsilon, then you can show that you get within epsilon of Poisson-Dirichlet 0.1 after 375 additions of uniform split merge in distribution, where you choose 375 to be a function of epsilon. So roughly speaking, that's what you do, and the challenge is actually showing that there's no dust, that cycles are generally macroscopic. Once you've done that, it's a sort of ghastly coupling argument where you color some edges blue iteratively to try and control the error, but actually the work's been done for you in the original Schramm paper there. Okay, I think I better stop there, but thank you for your attention. I was going to say 3, but that seemed too small.
So you said in a tree you get one cycle, right?
Correct.
And if you have one surplus, you get 2 cycles.
Yes.
So what's the distribution? So you're bounded by k cycles, right? If you have k surplus.
Yes.
But what's the distribution of the number of cycles? Such a cycle.
Of the number of cycles, I didn't say, and it's, I mean, it's quite complicated. As in, even for k equals 2, it's not a particularly nice calculation.
I mean, only 2 possible values, right? 0 over.
Right, but so if the configuration graph, sorry, so as in there are two, topologically there are 2 graphs you can have, and one of them definitely gives you 3 cycles, as in the first non-trivial, yeah, exactly, and the theta sometimes does, but you do have to know how you're orienting it, how you're orienting the kernel vertices. As in maybe we should study that more carefully, but I mean, part of knowing that it goes to Poisson-Dirichlet is saying that the number of cycles does diverge in probability for large k.